So our next speaker is Tal Shaharabany that will talk about what is where by looking, weakly supervised open world phrase grounding without text inputs. This is joint work with Yoad Tewel and Lior from Tel Aviv University.
So thank you very much, Professor Jerris. Hello everyone. Today I will present my work together with Yoad Tewel and under the supervision of Lior Wolf. What is where by looking? Weakly supervised open world phase grounding without text inputs. And let's start with the philosophy questions. What does it mean to see? If you would ask David Marr, which is one of the forefathers of computer vision, he would say, the plain answer in Aristotle would be to know what is where by looking. In other words, vision is the process of discovering from images what is present in the world and where it is. And what are the tasks and the benchmark that related to see, or the character of this watching and understanding images. And so we divide the landscape into three main features, which are open world, whether it's vocabulary, close categories or not, weakly supervised if we are using local annotations, and purely visual. So the fundamental task of C is object detection, where we have closed sets of objects, categories, and we use local annotations, and we only use the image as an input. And we have the task of phrase grounding, where we use input text, and therefore this is an open vocabulary, open word. But we use a weakly supervised. We are using local annotations, and therefore it's not a weakly supervised. And we use image and text, and therefore it's not a purely visual. And we also have the task of weakly supervised localization, where we use closed categories, but it's a weakly supervised task, which means that we only use a global label. And this is a purely visual, which means that we only get the image in order to describe the localization. And the weakly supervised phrase grounding, where we don't use local annotations. Local annotations means that we are not using any bounding boxes or mask during the training. And how does common algorithm for weakly supervised phrase grounding looks like? We usually take image encoder and language model, and we align the representation together, and then we generate a localization map, and we describe a bounding box from the localization map. In our solution, we use the text encoder of clip, and we use, and we call our generator G, and we use the image encoder based on VDG, and we use a decoder that align the clip dimension together with the visual representation, and then we generate. And how does it look like? So we have the, as I said, the text encoder, and the text encoder are aligned together with the visual representation, such that the text embedding just move forward the latent space and just multiply, and we calculate the cosine similarity between each vector in the latent space, in the visual, together with the representation of the text. And then we get the similarity map, ZS, which weighting the visual representation and we use the decoder in order to reconstruct the localization map. And we proposed 4 losses. The first loss is the foreground loss, where we multiply the image with the localization map. And we want that the foreground image and the text will have a very high score, a clip score, which is the cosine similarity score. And also the background loss, where we want that the opposite localization maps multiply with the image will be with a low score clip score. And we also use the explainability map of clip, which means that we take the image and the text of clip, and we generate explainability map that explain what are the pixels that related to the most related to the text. And we saw that the explainability map mostly focus on discriminative parts of the image instead of capture the whole shape of the object. And therefore, we start with guiding with the explainability map, but we also add the foreground and the background, which will help us to capture the whole shape. And we also add a regularization to the mask, to the localization map, in order to be more sparse in the mask. And after we solved the weakly supervised phrase grounding, we saw that there is a point in this landscape that's not been used yet. It's the task where we are open world, which means that we are not restricted with a closed set of categories. Of course, we are weakly supervised, which means we're not using local annotations, but we only get the image, which means that given an image, you need not only to generate the localization of the object, but also to describe the objects. As you can see here in this example, you can see a woman running in the street at the Capitol building in Washington, a woman in a red dress. So this is what expected from algorithm to generate. And how does algorithm, a common algorithm should looks like? So usually we need to generate proposals, region proposals of the objects, and then we need to use a captioning model, and then after using the phrase grounding model, we use the image and the captioning in order to describe the image. And we propose a baseline algorithm, which use a selective search. And then we use bleep model, and we cluster similar descriptions. And we use the same phrase grounding model in order to generate the localization and the objects. We also test our objects, our algorithm for weakly supervised object localization and phrase grounding, and also on the new task. And this is a visualization, and I want to talk about another property of our model, if we have enough time, and we do. So as we saw in the model, we take the representation of the text and we take the visual features, and we just calculate the similarity map between each region in the latent space. And we want to explore the visual features with each other's different pixels in the latent space. So we took every single vector in the latent space and generate and find the self-similarity with the visual features in order to get the self-similarity, the similarity map for each pixel in the latent space. And we found a very interesting property. We find that we get a very good localization map, and we found that the same object can be, for the same latent space vectors for the same object, we can find that the similarity map are more accurate. So here we can see that for the human that jump in the air, if we take the green representation in the latent space, and also for the green dot, we can get that there are very high similarity. And we use this heuristic in order to improve our model. So here we generate with G, the former weakly supervised network, we generate a map which is less accurate. And we also generate the self-similarity map, and we take the k-relevance map, and we define relevance for overlapping with a G solution to get aggregate solution, and we train the model in order to improve them and fine-tuning in order to get a G++ from the self-similarity map. And we use this fine-tune in order to improve G. So the next steps for our project, it's to make WWBL, which today it's divided to two phases. The first phase is to capture the objects, and the second is the phrase grounding. So in the next projects, we want to do it end-to-end. And we also look for zero-shot, closed-set segmentation, and video segmentation. So thank you very much.
Thank you very much. Questions?
Hi, first of all, fantastic work. And one question, did you have any ground truth for the maps? Because I saw that the data sets used have both captions and images, but was there any ground truth to the heat maps you
During
used?
the training or?
During the training, yeah.
Yeah, so it's weakly supervised means that you don't have the ground truth. So you don't have the local annotation. Local annotation means the ground truth. So we only use the text. Text, it's the weak supervision. It's a global label, so.
Thank you.
Okay. So,
And we believe that the power of text and image, if we train a model such as CLIP, and you can describe the all objects and the localization without the local annotations, and still be accurate. This is the main idea.
okay. Thank you very much. Let's thank the speaker again.